First of all, I'd like to thank the organisers, NFSTC, for inviting me to come and speak this week. I'm finding Florida exceptional, I have to say. In the UK, we have a reputation of having rain all the time. I don't think we've seen a decent bit of sunshine since about September. And I made the mistake of going for a walk down the beach for an hour, and bits of me have got burned. But anyway, there we go. It's been a really quite nice weekend so far. We'll see how this goes. What I'd like to do is to talk very much in general terms about DNA mixtures and deconvolution of mixtures. Reflect back, I think, on some of the talks that went on earlier today. When I saw Jack's, I thought, oh heck, he's just delivered my talk. But I think there's bits we can work around, and if there's any questions, towards the end of this week, we can take all of those questions, work through some of the mixture analyses. Mike's just mentioned, actually, we did have a conversation yesterday lunchtime. We were drinking tea, or I was, and he was drinking a vile-coloured fluorescent pink lemonade. But we did go through, if you take a look in your folder at some of these profiles that have been generated, I know they're artificial mixtures, but just look how good these new multiplexes are. I've been dealing with, through my career up until last July, with SGM Plus largely, and we've got het peak imbalances of 60%, 70% if we have a good day. You look at some of these identifiler and the hot start, Promega hot start kits, they're phenomenal, absolutely phenomenal. I'm aware of some of the work that Jill Tully and others have done at the FSS on the new ESR, the new Promega ESI, ESX kits. And again, the sensitivity of these new kits and the peak balances are just tremendous. So over the course of really just the last couple of years, the way this technique has moved on really means that we have a tool today which means that you guys ought to be able, I'm out of it now, I can just talk about this theoretically, but you guys have really got some tools that you can use to get to grips with some of the most obtuse, the most interesting, maybe the most difficult sorts of casework there is available. And before I came over, I was talking to Tim Clayton. He very kindly came and gave a talk for us at the university I'm now working at. And I asked him about DNA mixtures and his approach. And he said, it's easy, Chris, really, really easy. I've got this big pile of cases which are very straightforward. I've got this big pile of cases which are total and utter, well, they're difficult to do. We're not going to do anything with them, so I put these over here. I've got this little pile in the middle. And these are the ones that cause me the grief. So, we're going to concentrate on the little pile. Just think about this great big pile that disappears one way, another big pile that disappears the other way, and think the problem you've got actually maybe isn't that difficult. Okay, let's make a start. Oh, okay, a disclaimer. So, what am I going to talk about? I'm going to talk about mixture models, mixture analysis models. And we've got to realise that when we're doing mixture analysis, we are dealing with a model. We're dealing with something to hang the approach and to hang the mathematics off. And models are inherently, well, some challengeable. Models can be challenged as they're wrong. My model's better than your model. Sorry.
Let's check and make sure I did your right presentation.
You put the right one up.
Are you sure? I don't think I did. Sorry, I think I loaded the wrong presentation in. Bear with me.
So am I doing yours, John?
Which one? Yours is on the desktop. Didn't we put it in here?
No, it's not in that folder. It's on.
Oh, that's right.
There.
Okay, we're all better now.
Okay, it starts the same anyway. So, as technicians. So it's the same slide. We're going to start with models, and models are inherent in that, they have parameters, they're just models, they will give you an answer. Change your model and you will get a different answer. Excuse me a moment. Or if not necessarily a different answer, you will have a different approach. And you've got to realise that models have pros and they have cons. They have good points, they have not so good points. So we're going to start with looking at that. Then I'm going to move on to how do we recognise a DNA mixture. And it might sound very simple, but actually it's the process that needs to be embedded. How do you go through? You start with a profile. Am I looking for extra peaks? Am I looking for peak imbalance? And what can cause these things? Because it's not just the fact you've got a mixture, that you can have those things. Then how do we resolve a mixture? Do we need to consider how many contributors you've got? A mixing proportion. It's been mentioned several times before. Mixing proportion, mixing ratio. We'll go over that. Component pairing. What do we pair together? Which combinations are we going to consider? And because you've got this fantastic tool, because you've got such marvellous STR kits, can we use the quantitative data to eliminate or to include certain combinations of individuals or contributors? And then why? Why on earth are we going to do this? Why are we going to tackle this little pile in the middle? Okay, what was it Chris Bonington said? Because it's there. But it does occur. DNA mixes do occur. Most often, as forensic biologists, you're going to see them in sexual assault cases. Mixed body fluid stains, semen and vaginal mixtures, semen and blood mixtures, semen and saliva, saliva and blood, blood on blood, all of these things. In violent crime and homicides, you'll see overlapping blood stains. I don't know if any of you have actually tried taking one of your worn shirts and actually just doing a fatty bass test down the front, fast blood, just to check for saliva, and seeing on how many times you actually got a spray of saliva down the front of your shirt. Okay, maybe it's me just dribbles, I don't know, but you find the wearer themselves down the front of the shirt. So if you've got a blood stain there, you might pick up a DNA mixture. In property crime, I don't know about burglars in the USA, but it seems to be that in the UK, people who go burgling in pairs will stand outside getting themselves worked up and they'll, whatever they're doing. But we get shared cigarettes and you get multiple profiles from cigarette ends. And in drug crime, people share needles. And you may be asked to determine whether, in fact, two individuals may have shared a needle. So there's lots and lots of cases out there that's going to involve mixtures. And they can be quite complicated. What if these two people who go burgling are brothers? Think about that one. Okay, you saw this earlier. Yeah, I lifted this from John's book as well. I've got a copy upstairs which he's going to sign for me, but he doesn't know it yet. And it's originally, again, come from Tim, I think. And there's different approaches we can take to looking at mixed DNA profile. The so-called frequentist approaches, exclusion probabilities, random and not excluded, and so on. That was developed further in the 1990s. Bruce Weir, again, used a qualitative approach, but with a likelihood ratio background. And then there's the other methods where we use both qualitative and quantitative data. The binary method, which I'm going to talk about mostly today, and as been mentioned, the methodology is moving on, largely with computational support from computer programs, into a continuous model. Now, I'll hopefully be able to at least put some vague idea what a continuous model does. And I can't stand here and tell you what the maths is, because frankly, I don't know. John might be able to, no? No?
Sorry, Chris, I was 100 miles away.
Oh, that's all right. Don't worry. It's continuous model mathematics.
What about it?
Can you talk about it?
Not voluntarily.
Okay. So, let's get some terminology out of the way. We divide these methods up into whether we're using qualitative information or qualitative and quantitative. And qualitative is simply which alleles are represented. And that may not be, it may not be as simple as that statement says. You know, what is an allele? We'll get into that at some stage. And the quantitative information is how much of each allele is actually present. And what does that mean? Okay, so there's just me circling. I've got qualitative methods ringed in red and the quantitative methods ringed in dark blue. Now then, I don't like standing here talking with mathematical symbols on boards, but we've got to make a start somewhere. And a methodology that has been used and is used largely in the States is probability of inclusion, probability of exclusion, CPI, CPE, or random man not excluded. All these terminologies work around essentially the same thing. At any given locus L, the probability of inclusion, PI, effectively equals the sum of all the allele proportions that are represented squared. And the mathematical formula is given there. It assumes we've got a full representation of alleles. And therein is the question. How do you know you've got a full representation of alleles? Who's going to make that assessment? When does a stutter or an apparent stutter become an allele? And Mike has talked at length now, and Jack this morning, about thresholds. And we all work with validation sets, and we all are supposed to determine whether an allele's an allele or a stutter's a stutter. And we all have cut-off values. But again, just in the last talk, Mike mentioned this business of falling off the cliff. You know, if you've got a 15.5% peak, 4 base pairs before your main peak, is that a stutter, which you might normally cut off at 15%? Or is it an allele? Or is it a bit of both? So who's going to make the decision? And it also, theoretically, only covers those populations which fall into Hardy-Weinberg equilibrium, or as Todd said this morning when I talked to him about this, ish, sort of. And the probability of exclusion at the locus L is 1 minus the probability of inclusion. I'm sure that those things are familiar to you. So just a quick example. 3 alleles at a locus, each with a frequency of 0.2. You do the sums, the frequency, the calculation comes out at 0.36. 36% of those individuals will have an allowable genotype at this locus. And as Jack pointed out this morning, this is no different to dealing with blood groups. Going back to the beginning of my career, and ABOs and PGMs and EAPs and so on. But actually, when you work that through, that equals the sum of the frequencies of all the allowable combinations, the AA, the AB, the AC, the BB, BC, and CC. So it kind of makes sense. Now then, pros and cons of this methodology. It's been stated several times, it's an ease of computation. And again, I'll stress, it's computationally easy if you know that you've got full representation of your alleles. It's computationally impossible if you've got something you're not sure about, and therefore you lose information because you strike out that locus. It's claimed there's an ease of explanation in court. I'm just writing down, I'm just telling you what's there and who can be excluded, and my guy can't be excluded. What does that mean? If he can't be excluded, does somebody read into that he's included, and because he's included, it must be him, and therefore the probative value of that statement far outweighs what it actually means? Or do the jury take it meaning far more than it should do? There's also been statements that this methodology is generally conservative, and I spent some time with Todd and the other guys last evening drinking not tea, and we discussed this, and I think Todd has got an example of an instance where this methodology is not conservative. Okay. Disadvantage is, okay, we've labelled the point we need to have full representation of the alleles, and that depends on the allele calls and the effects of what a stutter is and other little bands you might find. But the biggest issue is that it discards the information contained within that DNA profile and this fantastic tool you've been given. And of course, I think it was Mike mentioned that NRC2 say, well, maybe that's a reason for trying something different. Maybe that's a way of, a reason for trying a different technique. So we move into the Bayes approach. And, okay, there's a little bit of mathematics up there, which I don't know how much you guys know about odds and probability, but they're relatively straightforward little equations. The first one, the odds of any event A equal the probability of A divided by the probability of not A. So the odds of something happening are the probability of it occurring over the probability of it not occurring. Seems straightforward. And if you do a little transformation of that equation, it's the probability of A divided by 1 minus the probability of A. And the probability of A can be converted back into odds over, it's the odds of A over the odds of A plus 1. John said I had to sing that, but I'm not a singer. I'll let him do that tomorrow. Odds of A, okay. Now the Bayes approach requires us to define two hypotheses. The whole issue, we go back, the whole issue here is I've got to have a probability on my top line and a probability on my bottom line of two hypotheses, the probability of something occurring and the probability of something not occurring. And that's normally defined as a prosecution hypothesis and a defense hypothesis. And the prosecution hypothesis is usually really easy to determine because that's the task you've been set. What's the probability of this evidence given this man left the semen? As opposed to the defense hypothesis, which is what? Somebody else left the semen? I don't know. I mean, defense lawyers talk to you guys when you're actually doing your work and give you some clue what the defense might be. Doesn't happen in the UK. So in using this technique, you've actually got to sit down and have a good think about what are reasonable alternatives. And you may have to find, or you may find that you have to change that opinion or change those hypotheses when faced with some further information. And in the UK, the statements make it very clear, the witness statements make it very clear that we've made a particular second hypothesis, and that they usually end with saying, and given any further information, I reserve the right to change, to review this statement and change my opinion if appropriate. POI in this instance, person of interest or suspect, whichever phrase you want to use, hypothesis for the prosecution, HP, the person of interest is the donor of the DNA, HD, the person of interest is not the donor of the DNA. And this is a representation of Bayes' theorem. And this is what the juries do to evaluate the scientific evidence under the hypothesis posed. Even if they don't know this is what they're doing, this is what they're actually doing. So the probability of a hypothesis given the evidence, the prosecution, top line, probability of the prosecution hypothesis given the evidence divided by the probability of the defense hypothesis given the evidence equals that term in the middle times the probability of the hypothesis prosecution and the probability of the hypothesis defense. That last term is the odds before the scientific evidence. That's what the jury's heard before you walk into court. That's what the jury's heard in the statements from the police officers or the summing up from the opening speeches from prosecution counsel and defense counsel. They've formed a view. That's their prior odds, if you like. In my view, given what I've heard already, this guy is, or whatever. That term is what they're actually debating. How good is what's the probability of this prosecution hypothesis given what's put before us, divided by the probability of the defence hypothesis given what's put before us. And that's influenced by the term in the middle. That's modified by the scientific evidence. And that term in the middle is how you put your scientific evidence. And that's your likelihood ratio. And it's just an expression of the weight of that scientific evidence. Everybody okay with that just now? Okay. So how do we put it into words? This is one of the biggest issues, and one of the things that scientists will debate between themselves, and scientists will debate with lawyers, and lawyers will disagree vehemently about everything, because they do, that's what a lawyer is about. So how do we actually put this sort of thing into words? What's the probability a semen on a vaginal swab came from our suspect? But we mustn't forget that in each of these cases, we're considering the evidence. We have to focus on the evidence, the fact we've got, a DNA profile. And we have to, if we start talking about the individual or the crime, we can then be accused of transposing conditionals, and we get ourselves into trouble, and we get appeals, and it doesn't go well. So we have to consider the probability of the evidence given the hypothesis we're taking place. And we have a set of numbers. So we have a likelihood ratio, which is a number. And if we look at the top there, I'm not sure how does this work. Well, it's a bit faint. But anyway, we could have a scale for our likelihood ratio. It could go from a likelihood ratio of 1, which was equally balanced. Don't forget we've got a prosecution hypothesis, evidence, the probability of the evidence given hypothesis P over hypothesis D. If those two hypotheses are balanced, we get a likelihood ratio of 1, and all your work is effectively inconclusive. Doesn't add one thing or other to the deliberation the jury is making. As we go positive, and in terms of powers of 10 positive with that number, we provide increasing support for our prosecution hypothesis, for the hypothesis on the top line. As those numbers go to powers of 10 less than 1, all we're doing is saying that actually the number on the bottom, we're actually providing evidence to support the defence hypothesis. That the evidence is actually providing more support for the bottom line rather than the top. And this is a continuum. It doesn't just fall out as 1 million or 100,000, but there's something in between. But we've got to find some way of expressing that for a jury, because it's our job to actually put some weight in this and to advise. So what do? We have a set of verbal scales, and these have been debated long and hard, from extremely strong. What does moderately mean? Or limited? They're words. We have to find some way of creating a scale in words that matches the numbers that we're comfortable to explaining to a jury. Now, I had the privilege of starting my career in DNA profiling in about 1987. When we had multilocus probes, I guess it was a bit seat of the pants sort of science. There's lots of validations and so on, and we're all well trained. And I remember getting lectures from Alec Jeffreys and so on, and telling us what a brilliant technique it was, which he would do, of course, since he invented it. But anyway, we ended up with our autoradiographs, which could take 12 days to develop, and then we might have to sort of peer a bit, just to check where the bands are. I don't know if has anybody done multilocus probes and autoradiographs? One in the front, good man. We had to be able to look at these things and then give an estimate of the weight of the evidence. So we would look at the top 11 bands, and on the basis that a band might occur in a given position with a probability of 0.25, and 11 bands gave us 1 in 2.7 million, And the phrase that went with that, the semen came from him. We had no problem with it. The court had no problem with it for at least a year, you know. And prior to that, of course, if I'd got a blood grouping result with 1 in 400, that was fantastic evidence. That was brilliant. You know. Now, anyway, 1 in 2.7 million. Then the statisticians got involved. And it all went downhill. No, that's not true. So, but we end up with a scale, a verbal scale with which we can talk to juries and to lawyers to express what we feel about the weight of the evidence. And it's really quite important that, you know, people get to grips with that. Okay, something might be challengeable, some people might debate the words, but you've got to have some sort of scale. Right, okay. So, the interesting thing then is we debated, or we started a discussion about what's the defence hypothesis. So let's take the standard case. You have an alleged rape. A woman alleges a man had sexual intercourse with her. The sample you've got is a vaginal swab, or because I'm in America, it's a vaginal swab. But anyway, we have this situation where we've got a known contributor. We have an intimate swab from this woman. Would you expect there to be DNA from her on that swab? Those who think no, would you put your hand up? Okay. So we'd expect there to be material from that woman on that vaginal swab. And let's say the prosecution and the defence agreed that's likely to be the case. So the prosecution hypothesis is straightforward. We've got the evidence, the mixed DNA profile, because it consists of a mixture of the woman who donated the swab plus the man from whom the semen came, our suspect or person of interest. The defence hypothesis might be we accept the woman's DNA profile will be there, but the other profile came from someone unknown. And then we go back to, for each locus it's relatively straightforward, because if we've got a profile that only contains 2 people, and both of those individuals are properly represented in whatever proportion they are, then the top line becomes 1. The probability of this evidence, given that scenario, is 1. And the bottom line is, well, we accept the woman's there, so that bit's 1, and the probability of that other element of the profile is either p squared or 2pq. So it's 1 over 2pq. Straightforward. But do we know what the defence hypothesis actually is? What if the hypothesis is it's not that unknown, but it's the suspect's brother? Doesn't that put an entirely different complexion on this? And that's the sort of thing you may have to face. You may make an assessment, and you may make a judgment about what an appropriate alternate hypothesis is, but you may need to change your calculations, and you may need to change your conclusions depending on what the defence come back at you with. And what about that one? Okay, again there's an allegation of rape, but the woman's had consensual sex with a boyfriend at some time, and you've got a 3-person mixture. And again, your first hypothesis is, your prosecution hypothesis, it's vaginal material from the woman, plus semen from the boyfriend, plus semen from the suspect. B plus S on the top line. The defence may say, okay, we'll accept the statement that it's the victim and the boyfriend, but then they'll want the unknown thrown in there. They might not accept the boyfriend's in there, and they might want 2 unknowns, and it makes a difference to the numbers you'll see. As I say, the alternate defence might be victim plus unknown 1 plus unknown 2. And when you get into these types of calculations, that second hypothesis is interesting. What I have done in the past is actually look at the issue of a known 2-person mixture, where I know I've only got 4 alleles at a locus, and whatever locus you look at, I've clearly got alleles which are well above any sort of threshold. I know I've got no dropout. I've got a perfectly good profile, mixed profile, where the defence have said, well, we actually think you've got another individual in there. So they'll take a 2-person profile, 2-person mixed profile in effect, and they'll say, I'll have victim and unknown, victim and suspect on the top line, and victim and 2 unknowns on the bottom line. You can do that calculation. What tends to happen is that your evidence gets stronger. The concept of just the idea that I've put more people in the mix, you know, my likelihood ratio goes down and I get a weaker result, isn't true. What I found was that as those analyses were put forward, and I've only got a two-person mixture, the likelihood ratios go counterintuitively, they actually get bigger because it's less likely to explain four alleles autologous by having 3 people. It's a bit counterintuitive, but if you get into this and start playing with the maths, you'll see that's the case. Right, after that little digression, I'm going to talk about the binary model. This is the standard model has been mentioned several times this morning. It was first described by Tim Clayton and others in 1998. It really is a great methodology. It uses both the qualitative and quantitative data contained within your DNA profile, but it does require a very detailed knowledge of the performance of your STR chemistry, and that comes from a very detailed forensic validation and knowledge of your casework performance, how these things work in actual casework. It's been mentioned in several of the talks today. The first part of the method is to assess the quality of the profile, to determine, and that's really important, I'll come back to that, to determine the number of contributors, make a best estimate of the number of contributors you've got. You then list out all the possible genotypes, and I have an exercise. I wish I just had enough bits of paper to make you guys sit down and write all these things out. A, it would serve you right, and B, you know, it is actually a very valid exercise to be able to sit down and work out these combinations. If anybody wants to do it, I can print off the sheets, you can have a play. We generate a set of retained genotypes, ones which we are confident, given the information we have in the profiles, the alleles present and the respective contributions in those. If you then determine that a particular combination can't be retained, or if you see that amongst the retained lists your suspect is not represented, he has to be excluded. There's no saying, well, you know, I could count him in here and I could count him in there, but actually when I get to this locus and this locus and this locus, he doesn't really appear. We'll just have a think about that again. If he's not in that retained list throughout the whole profile, he's not there. The general principles apply to any of the STR chemistries. I guess, I haven't looked at it, maybe even WISE as well. I guess it works with WISE as an STR chemistry. There are 3 basic assumptions that are being made. All models are based on assumptions, so you've got to know the assumptions you're making with the modelling. The peak heights or peak areas are proportional to the amount of DNA present. The more DNA, the bigger the peak you get. And does it matter whether you use peak heights or peak areas? Well, frankly, it doesn't. It's normally considered that the peak area is a better representation of just how much DNA is there, which is fine if you've got a really nice peak, which is, you know, got a nice morphology and it's a decent amplification efficiency. When things start falling, when the peak heights start going down, when you start getting to the point where you're a bit unsure, you get below various thresholds, whatever these thresholds happen to be, 100, 150, and the peak heights go down and they get slightly broader. The way the software, the genotype or whatever, GMAP or IDX, actually looks at a profile, it's only that profile, that EPG, is only a mathematical representation of a signal that comes out of the machine. It's interesting if you go through it and see how much smoothing goes on, how many data points actually get merged together. So what you're seeing as a nice peak is actually a representation of something else anyway that's been manipulated before you even see it. So the other thing is that these particular bits of software have algorithms which tell them when to stop a peak. And it depends on the rate of change of the data. And as these peaks go lower, that gets a little bit flakier. So the peak doesn't quite know, the software doesn't quite know where to cut off the peak. So at lower levels, the peak area might not necessarily be a true reflection of the amount of DNA. It'll be good. All of that ramble sort of comes down to really it doesn't matter whether you use peak height or peak area, it's all the same. So that's that. Mixture proportion. The mixture proportion, or probably easier sometimes when you inspect a DNA profile, the mixture ratio, what proportion is the major to the minor? 1 to 1, 2 to 1, 1 to 2, 10 to 1, 1 to 10. The ratio is easier to see. The mixing proportions takes a bit of a calculation, but a lot of the mathematics and the software that supports some of this works on mixture proportion. But you would expect with a decent amplification that it's roughly the same across all loci. So if you're looking at D3, you know, you're looking at a 1 to 5 mixture. If you're looking out at FGA, it's still roughly 1 to 5. That doesn't necessarily hold when you get lower level mixtures, and that can be an issue. And the final thing is if contributors actually share alleles, so they share some element of that DNA, the peak heights or peak areas are cumulative, and this is known as dosing. And well, I'll show you one or two of these things later. And I say, I keep harping on, this requires a detailed knowledge of the performance of your STR chemistry, which comes from your detailed forensic validation and your casework data. We're nearly getting there now. All of this gone before. We're nearly getting to what we actually do. Tim calls this the 3 R's. Recognition, first thing. We have to do an appraisal. Somebody has to designate alleles. And I'm going to ask this question before I put the next bit up. In how many laboratories do you have dedicated DNA units where the alleles are designated by the DNA staff? Wow. So all your reporting officers are actually doing all your own designations. Is that correct? Yes, Chris? Does anybody have a dedicated DNA unit where they allow the analyst to do the designation? Wow.
Yeah, I mean, if you've got microvariates, things like that, yes.
Yeah.
Artifacts, things like that, yes.
Okay. Okay. That's fascinating. Okay. So somebody makes a designation of an allele. It might be in the UK. It'll be an analyst. Somebody has to recognise there's a mixture, and that tends to be the reporting officer, and make an assessment of the profile quality. So we have to recognise what's going on with our profile. Once we've decided we've got a mixture, and once we've determined what our profile quality is, we can then start thinking about how we go deconvoluting this. And it gets really boring now because what we do is we list all the genotypes, generate the retained list. Is the genotype of the suspect a contributor amongst that list? If he's retained, yes, you do a calculation. If he's not, you exclude him. And in the reporting, you formulate your hypotheses, you evaluate your strength of evidence, and you report it with whatever standards you have in your laboratory. I'm not going to talk about reporting. We might pick that up if you want later in the week. So how do we recognise a mixture? Well, we'd normally say it's the presence of extra bands. So does this always indicate a mixture? What about those instances where you just see an odd allele at 1 or 2 loci? Is that a mixture? Is there something else going on? Is it possible with a mixture? So if I've got a mixture of 2 people, is it possible you'll only ever see 1 or 2 alleles at a locus? Is it possible? Is it likely? Oh, okay. So an extra band is a fairly good indication you've got you've actually got a mixed profile. But there are other things that might actually give you extra bands, and we'll come on to a little biochemistry refresher in a minute. The second thing is there is pronounced heterozygous imbalance. Okay, that allele A and allele B don't actually sit together as sister alleles, and there's something else in there. And Mike's gone through that at length on several of his talks today. But there are other reasons why you might get heterozygous imbalance. And if we go into biochemistry, additional bands, it's not a great representation, but you see where I'm coming from. You get issues with the tack. It goes on, it falls off, you get bits of folding, you get these extra bands, 4 base pairs lower than your main peak. Seem to be fairly consistent, but we know we call them stutters. Depends on how high they are, and that the height depends on the particular amount of amplification at that particular length. If it was Mike, I think, mentioned the fact that the length of repeat unit, particularly the simple repeat units, the longer they got, the more chance a particular allele would stutter. Stutter is not the function of a locus. A stutter is a function of the allele, and it will change across that range, and it will change. The longer alleles tend to stutter more as long as they're simple. I did have a picture somewhere of Tho, where you suddenly got a 9.3 and the rate of stutter just drops through the floor because of that 0.3. You also have the issue when you're doing your processing, you add a little time at the end so that you get additional adenylation and everything gets converted from the N peak to the N+1, and if your system isn't as good as you might be, you might get extra N peaks. So you might get extra peaks for lots of reasons. You might get an electrophoretic problem where you get pull-up, where under here I've got blues pulling up greens, greens pulling up yellows, and you might get extra peaks there. You've got to recognise them, straightforward. You might get additional bands because of chromosome abnormalities, allelic mutations. There might be duplications, trisomies. We do see trisomies. They tend to be 1-to-1-to-1s, so they're relatively easy to recognise. You do sometimes see, with hairs in particular, potential somatic mutations, mosaicisms, where a particular cell or cluster of cells is mutated and you get a bit of extra. So we get chromosomal rearrangements, rare. We get trisomies, D21s. We get issues with imbalance because we get trisomies at the sex chromosomes. We get a bit of extra, an XXY and a Klinefelters. We might see those more often. And if somebody said to you, well, just have a look at a melogenic to see if you can see an imbalance, these occur far more frequently than you might expect. And a simple imbalance at a melogenic may not indicate a mixture. A mutation within a simple single cell, the somatic mutations, may be tissue specific, as I said with hair. They're more common than the 1-to-1, and they often show 3 allelic patterns. And there's a mechanism for you. So you get a bunch of cells for both 11-14. Somewhere in the growth process, one of them changes, that's disappeared, one of them changes to 11-13. When you take your sample, you take a small proportion of population of those cells which are actually 11-13s, not 11-14s. So you see a 3-banded pattern, and 4-to-1-to-3 instead of 4-to-4. Everyone happy with that? And you do see them in real life. So we've dealt with extra bands. We're pretty confident if we've got more than 2 bands at a locus and they're decent bands, we've got more than one person involved. And the interesting thing there is, what phraseology to use. I've got a single source sample. Okay, those little bits and bops in the background, are they just odd bits of DNA that have been popped up from somewhere, or is that a second person? We've had quite a lot of difficulty in the UK certainly since 2007 and the Hoey trial and the Omagh bombing about the low template DNA profiling. And where individuals who've come along as defence examiners have gone into the baseline and said, well, I can see extra bands in the baseline. They're above our noise, signal to noise ratios, the 3 standard deviations. We think they're peaks. But actually, they're below the 50, so they haven't been called as alleles. But you've ignored them, which is wrong. So that's the one aspect. There might be the real perpetrator sat in the baseline. the same group have come back and said, well, because you haven't used that technique and you may not have found these, you may not have actually found the third untrue individual. So it's both sides of the coin. It made it quite difficult to deal with that sort of thing. So, okay, we've got extra bands. Pronounced heterozygous imbalance. It's effectively unequal amplification efficiency, attack. If you've got bands which are at one end of an allele range and the other end of the allele range, they might get amplified slightly differently, so you get peak imbalance. You might get degraded template DNA. We haven't mentioned that yet. What happens if you amplify a degraded sample? You get a sort of ski slope. What happens if you've got a mixture in that as well? Stochastic variation, if you're working at very low levels, as Mike pointed out, you might pick out different numbers of starting template, different numbers of cells in the first instance, and finally you might have a primary binding site mutation. There's the ski slope effect I just mentioned. The amplification efficiency varies from low molecular weight to high molecular weight. The peak imbalance is marked, very marked. Second greens, first blues, you can see the peak imbalance marked. And particularly down here at the D2, you've got the second blue peaks hidden sort of behind that thing that controls the PowerPoint. But you've got a very marked difference at that locus. And my issue then is, if this is a mixed profile, and in fact my second component is fairly steady and sits around about the point of that line, just over 200 RFU, at some point, my minor component at the D3 end becomes my major component at the D2 end. How on earth do we deal with that one? I haven't got the answer. Low template DNA, that's been gone over again by Mike. We may get stochastic variation. Primer binding site mutation, we get partial binding of the primer, and we get a peak imbalance. If there's no primer binding, if it's a real problem, we get a null allele. And it can be detected if you're suspicious of that, clearly, by going to a different chemistry. And that's the sort of thing you see. Now, if that's mixed in with something else, how do we deal with that one? So just to recap, is it mixture, extra bands or peak imbalance? We make an assessment of the quality of the DNA profile. The amplification efficiency, is it degraded, is it low-level mixture, and does it matter? And we haven't mentioned this yet, but there's this term called conditioning, where you can actually look at your DNA profile and, given the case circumstances, actually determine whether you would expect one or other of the individuals concerned to be present. And only under those circumstances might you say, given these case circumstances, I will look at my profile first from my victim, and I may see whether I can subtract her from the whole and see what's left. If you don't feel you can do that properly, you don't look at your reference samples before you've done your mixture deconvolution. Rule number one, that's it. Because if you do, and Dr. Badoli comes along, he will accuse you of institutional bias. He will accuse you of, if you start looking at your references before you've done this analysis, you will be biased because it will be in your head. And that will be used in court. I guarantee it. Okay, classification of these mixed DNA profiles. There was the German group spoken about earlier, talking about type A, type B, and type C mixtures. Here's a different classification. A green mixture. Everything in the mixture is above 400 RFU. We are confident we've got every allele represented. There is no possibility of dropout. Every threshold we've got in our system has been exceeded. We're happy with that. We can go ahead and process it. This is this pile of cases over here. We then have the red peaks. Peaks heights below 150 RFU. The closer they get to 50 RFU, the more difficult it gets. We've got incomplete representation of alleles. We've got dropouts. We've got drop-ins popping up. When you get to that level, stutters go all over the place. You get exaggerated peak imbalances. Now, if we're talking about some of these nice new kits with peak balances of 85% plus. That's one point. SGM plus, peak imbalance, 60, 65%, okay. When you go to these low level, you have to start considering your peak balances could be 30%, 20%, 15%. And at least in a couple of instances, talking to Tim, they've gone down to less than 10%. So you've actually got, 90 to 10 and calling them sister alleles. It makes a huge difference to your calculations. It may be those go in the too difficult tray. Lots and lots of bits and pieces that could be stutters, lots and lots of bits and pieces that might have dropped out. So we're really concerned about the ones in the middle, the amber. Peak heights between 150 and 400 RFU. Your lab guidelines have to be pretty strict, but you've got to give you've got to give yourself a little bit of leeway. You can't actually consider an 85% peak imbalance when you've got something at 150, 200 RFU. You've got to actually allow more. And this again comes back to your validations, doing dilutions to see what actually happens in your system for real when you do this sort of work. And the resolution, as we go through it, the second step, unless you're, this is the rule 1 warning, unless you're conditioning on a known profile, you do this without any knowledge of your profiles of any reference samples. If you can't condition on your female, if you can't condition on your male, don't look at them. Okay. Having said all that, I'm going to start by conditioning. 2 contributors to a mixture, would you agree? I've got 4 alleles. Nice, clean, even. Happy there's 2 contributors in that? Yes. What's the mixture proportion? Thank you, 1 to 1. That's straightforward. So, I'm going to give you one scenario. This is a vaginal swab from this rate we went back to before. The donor, the female, is 810. What's the genotype of the male? 911. Everybody happy with that? Good, that's the case finished. That's that pile. Inside front of underpants, scenario 2. The male donor this time is the 810. Can we condition on it? Is it reasonable to expect the male to have some material on the inside front of his own underpants? Yes. What's the genotype of the second contributor? 911. Notice I didn't say female contributor because we've got no information in this about the sex of those 2 individuals. What about the third scenario? If this happens to be a mixed body fluid stain taken from a carpet, can I condition on anything? No. So we have to go and do the full analysis. Good. So there is a logical progression for this analysis. We've been through it here, we've been through it, Mike's been through it, Jack's been through it. We're going to go through it again and again and again until you understand it and you do it all the time. We assess the minimum number of contributors based on the number of bands we see, or the number of alleles we see, because the bands could be different from the number of alleles. We then estimate the mixing proportion. We use the observed alleles to list all the pairwise combinations, and we use the peak height and area data and the mixing proportion to eliminate those genotypes which are not supported, and then we compare it, with the reference samples. How many contributors, please? 2? Yes? Okay. Oh, somebody said at least 2. Good. That's good. There's 2. Mixing proportion. What do you think that is? Okay, that's a mixing ratio. Mixing proportion is 0.75 to 0.25. Yeah? Okay. It's completely interchangeable as long as you realise what you're dealing with. Yeah, it's a 3-to-1 mixture, but that's the ratio, not the proportion. All the pairwise combinations, we'll do that in a minute. Oh, there we go, there's the answer. Yeah. So, those are all the pairwise combinations. How many of those do you think are actually allowable? Come on, you just told me what it is. 2, because we haven't said which is which. Effectively comes to the same thing. Major contributor comes down to 1418, minor comes down to 1617. One of these individuals is a 1418, one of the individuals is a 1617. What if your suspect had been a 14, 16, 17, oh, that's the right one, isn't it? No. What if your suspect had been a 14, 16 or a 17, 18? Would that have stood? Would you have eliminated him? If that's the only combination you've got left. Let's say 14, 16, yeah. I'd have been pretty pissed off if you'd left me in and I was that 14, 16, you know. Okay. If there are 2 contributors, maximum number of bands at any long locus should be 4, thank you. If there are 5 or 6 bands, what does it imply? More than 2. And we covered mixing proportions or mixing ratio beautifully there. Okie dokie, what about that one? 3 persons or more? At least 3. Next question, there's a peak there not labelled in the 19 position. What do you call it? Is it a stutter? Maybe. Is it an allele? Maybe. Okay, we're getting there. Is this a major 2020 with at least 3 others? Maybe. They're getting good at this, John. Or could it in fact be a 5-person mixture? A 1220, a 1320, a 1420, a 1720, and a 1920. And if you add all the numbers up, you know, you're not getting quite to 1,073. But could there be a 2020 on the end? Could that be a 6-person mixture with a 2020 as well? Lots of nods. It could be. Yeah, of course it could. And this is one of the issues when you get to these big majors, lots of minors. So what we've done there is actually covered the possibility there's some dosing going on, and there's, you know, mixing lots of individuals with a shared allele gives you that one whacking great peak. So the peak area height reflects the amount of template from each contributor. If the peaks are shared, if the alleles are shared, you get a dosing effect. And in a well-amplified green mixed profile, the mixing proportion is constant. This is a piece of paper you're supposed to have on your table, I had hoped, and you could do this. But shall I just fill it in? How am I going, Debbie?
You've got plenty of time.
Oh, okay.
You've got 45 minutes.
How many? Okay. 10 to 1, that's easier to say than 0.91. 5 to 1 is easier to say than 0.83, and so on and so on and so on. 1 to 1, 50%, fine. Okay, I'll fill that in. Everybody happy with that as a way of working this up? And on the other side, you have the complementary that are going to add up to 1. Everybody happy with that as a mixing ratio? What about the amelogenin? Because, you know, we've said you look at the amelogenin and you see the imbalance and you can give an indication of the profile, the proportions of each profile in there. 10 to 1 mixture gives you 12 to 10 X to Y. That's a 10 to 1 male, and so on and so on and so on. I'd really like to give people these sheets of paper, Debbie, and let them do these numbers for themselves at some stage. Okay. No, it's okay. At some stage, we'll print these off and you can all have a play. But it's a big class, isn't it? Okay, then. This is one I was, again, hoping you'd have a bit. This is like a bingo. If we've observed 4 alleles at a locus, A, B, C, D. Can you write out the 6 pairwise combinations you might see?
Yes.
I know you can. A, B, and C, 3 alleles at locus. There are 12 combinations, and I know I can't do that. I always have to look it up. I admit it. I'm sorry. I can't write it out at the top of my head. AB, 7 pairwise combinations. And the fourth one, AA. How many combinations would AA have? One, thank you. We assess each combination against mixing proportion, heterozygous peak imbalance, and we mark each genotype pass or fail, and we retain the genotype list. So I'll just whiz through those. Everybody should have got that. I guarantee that a big proportion, including me, wouldn't have got that necessarily, but that's what it is. 2 alleles autologous, there are 7, including the AB combination, and 1 allele autologous. For a 2-person mixture, both have to be AA. Now, there are bits of software around. This is one of which I was involved with for a number of years. This comes out of the iStream module of IQ, but there are other systems in play, and I think, Todd, you were talking yesterday about some things that you've got in the pipeline, and so is Mike up at NIST. And this is the easy way to do it. You put your data in a machine, and it spits these things out or into a program. In this instance, we can see 2 alleles autologous, the 7 combination pairwise combinations that make up potentially for that. Looking at prefamp, there's no prefamp between, there's no prefamp rule, mixture proportion rule yet fitted. You don't know what that is. Prefamp doesn't count with homozygotes. But effectively what you've done is you've gone through each of these exactly as we've just talked about. We've looked at, taken the 2 alleles at the locus, we've broken it out into every pairwise combination you might have. You've looked at the preferential amplification for each combination. Was 16-16 allowed, is 15-15 allowed? Does it fit with the mixture estimate you've got? And the mixture estimate here was around about 5-1 in this particular profile. And IQ would look across all loci and give you an average, a mean. And yes, you'd include a 16-16 contributor and a 15-15 contributor for this particular set of peaks. There's the peak areas there. 5.3 for the 15s and 24,000 for the 16s. So the 15, 16, 15, 16 fails on the peak imbalance rule. So that, I mean, those are really nice ways of putting these out and actually doing this calculation really quickly. If you're going to do this for 16 loci, for 2- and 3-person mixtures, or certainly 2-person mixtures is difficult enough, 3-person mixtures I guess would take you quite a long time. That particular illustration came out of profiles in DNA. There we go. Just to give an example, or perhaps I should have picked a different set of data, but in a continuous model, the one we didn't get to, where we're going next with all of this methodology, all of these combinations would be allowed. Your printout from your computer would give you every one of those as allowable. But next to them would be printed probability. So the probability of that top one would be close to 100%. And the probability of every one of those others, I guarantee, would be very close to 0. That's what a continuous probability model does. It never actually says this is excluded or this is included. Effectively, that's what binary means. You know, I'm going to make an assessment, that one's in, probability 1, that one's out, probability 0. A continuous probability model actually then just looks at all of the combinations and says, well, you know, 45%, 20%, and so on, all the way down. In this instance, I guess it's very close to 100%, and each one of those will be very close to 0. Finally, we've got to comparing with a reference sample. We've got this retained list, 16, 16, 15, 15. That's the only thing we've retained. Let's compare that with our suspect. Oh, guess what? He's a 16, 17. He's out. If he does match at one locus, you've got to go look at all the other loci. If it's confirmed at all the loci, you can't exclude him. He's included amongst that retained list. in processing this, you having done it all, I suggest strongly that one of your colleagues does it all again, so that they confirm your results. And I guess lots of laboratory protocols would actually say that's the way you do things. And that should be done blind, and that second scientist shouldn't have sight of the profiles of your reference profiles either. And as I say there's some of that analysis is built into some of the expert systems, not just iCube, it's built into other things as well. And as was mentioned this morning, there are potentially going to be, is it Excel-based, Mike? Is he gone? He's gone. Excel-based programs that NIST will put out in due course. So, whilst I might be very early, and I started very early, what I've done now is just outline some of the models, 2 of the models, mentioned a third that we've used, mentioned briefly the random man not excluded, those models which include only qualitative data, and the binary method specified really by Tim Clayton and others, in which we look at not only the alleles present but also the information contained within your profile. We've talked about how we recognize a DNA mixture, the extra bands, for all of the things I said about stutters, end bands, pull-ups and all the rest of it. You know, you've got to recognize when you've got an allele. That's what it comes down to. The het peak imbalances. We looked briefly at what other things cause artifacts, and the resolution of the mixture is a series of logical steps, and you must be objective, no sneaky peeks. Okay, I'm going to stop early, but thank you very much. I'll be around for the rest of the week, and hopefully we'll get into some of these in some detail later. Thank you.